Hello everyone, welcome to lecture 14 of PEC. We will discuss Y-delta transform in this lecture. After studying this lecture, in principle, for any two-terminal network, if it only contains resistors, we can transform it into the serial parallel connection of the resistors equivalently, and then analyze it easily. First, we will introduce star or Y network and delta network, as well as T and pi network. For such a three-terminal network, we regard it as a upside-down Y, so we call it Y network. While for such a three-terminal network, we regard it as a triangle, so we call it a delta network. Similarly, turn the Y network an angle, we can write it as a T network. Y network and T networks are equivalent completely. And likewise, turn the delta network an angle, we can write it as a pi network. Delta network and pi network are also equivalent. In the following discussion of this lecture, we will discuss that under what conditions the Y network and the delta network are equivalent. Here we need to firstly discuss the knowledge of the equivalence for the multiple terminal networks. In the previous discussion, we know that for a two-terminal network, if its port voltage and current have the same form and parameters, they are equivalent. This conclusion remains valid for multiple terminal networks. But for multiple terminal networks, equations of the port voltages and the currents are more than one, so it has a bit more to deduce. Next, let's take a look for the delta network on the left side and Y network on the right side. If all the equations of the port voltage and the currents for these two circuits are with the same form and parameters, in the condition that we don't know the internal elements and their connections, we say that these two groups of resistors in Y network and the delta network are equivalent. Okay, we deduce it little by little. For the delta network on the left side, because it has this node, so we may analyze it with KCL conveniently. That is to say, this current is equal to this current minus this current. The direction of this current is like this due to the direction of this voltage. The direction of this current and this voltage are selected to be associated. So we know that I1 delta equals U12 delta over R12 minus U31 delta over R31. Similarly, we have I2 delta equals U23 delta over R23 minus U12 delta over R12. And I3 delta equals U31 delta over R31 minus U23 delta over R23. These are obtained on three nodes with KCL. In addition, we can regard it as a generalized node. So we have I1 delta plus I2 delta plus I3 delta equals 0. Beyond that, we can also apply generalized KVL in this loop. I12 delta plus I23 delta plus I31 delta equals 0. These five equations are all equations of such a three-terminal delta network which we can get at present. Then we analyze the Y network on the right side similarly. For a Y network, because this voltage drop is equal to the voltage drop from here to here, so it's convenient to deduce with KVL. So we know that Y12Y equals I1Y R1 minus I2Y R2. Similarly, this voltage drop is equal to the voltage drop from here to here. U23y equals I2y R2 minus I3y R3. U31y equals I3y R3 minus I1y R1. And we use KCL at this node. I1y plus I2y plus I3y equals 0. Similarly, we use KVL in this loop. U12y plus U23y plus U31y equals 0. These are all equations for this Y network we can get. Recall that I said previously, that is, if the two circuits are equivalent circuits, their port equations need to have the same form and parameters. Let's take a look at this equation and this equation. They have the same form and parameters. The same is also for these two equations, but the trouble is that these two sets of equations do not have the same form and parameters. Okay, let's take a look. These are the equations for delta connection, and these are equations for Y connection. As we have discussed, this and that sets of equations do not have the same form and parameters. We can turn them into the same form and parameters. For example, we can regard 1y2, 1, 2, 3, and 1, 3, 1 as variables and solve them in this set of equations. So they can be turned into forms like this. With comparative analysis, we can see that in this equation on the right side, U12 is equal to what times I1 plus what times I2. In this equation on the left side, the R1 is this. The R2 is this. So if these two circuits are equivalent, it must be R1 equals R12 times R31 over R12 plus R23 plus R31. Similarly, R2 equals R23 times R12 over R12 plus R23 plus R31. And R3 equals R31 times R23 over R12 plus R23 plus R31. That is to say, this is the condition to ensure that these two sets of equations have the same form and parameters. So our equivalent transform is complete. Next, in turn, we can regard I1, I2, and I3 as variables and solve them in this set of equations. We can get such equations. We compare this equation and this equation. This equation is that I1 is equal to what times U12 plus what times U31, wherein this what is this. So we can write it as R12 equals R1 R2 plus R2 R3 plus R3 R1 over 3 R3. We can write it further to be R12 equals R1 plus R2 plus R1 R2 over R3. Similarly, R12 R23 equals R2 plus R3 plus R2 R3 over R1. And R31 equals R3 plus R1 plus R3 R1 over R2. In other words, if element parameters meets such requirements, these two sets of equations have the same form and parameters. That means that the two three-terminal networks are equivalent. Then let's sum up. If we want to transform a Y network to a delta network, there is a set of equations. In return, if we want to transform a delta circuit into a Y circuit, there is another set of equations. It is easy to remember these two groups of equations. You can see for Y2 delta, a certain resistance of delta connection is equals to the sum of the corresponding two resistance of Y connection and plus the quotient between the product of these two resistance and the opposite resistance. From delta to y, a certain resistor is equals to the quotient in which the sum of all resistance in delta connection is the denominator and the numerator is the product of the corresponding two resistance next to the resistance of the y connection. So it's also easy to remember, but we do not require to remember it. What we require is a special case, that is when R1 equals R2 equals R3 equals R, from Y to delta is 3 times R. In return, similarly, if R12 equals R31 equals R23 equals R, we know that in this equation, they are all 1 over 3R. So for the special case of the Y-delta transformation, it can be summed up as such a figure. The resistance of Y connection is always equal to 1/3 times the corresponding resistance of delta connection under the condition that all elements of Y or delta are the same.